Greetings and salutations! In this video, there are three important unit vectors that I want to talk about, which are called t, n, and b. Imagine the path of a particle in space. If you were standing on that particle at some point, what direction would you call forward? Forward is not a permanent direction like the positive x-axis. It can change depending on your orientation. But forward is always the direction we're facing, and so we can define forward to be the direction of motion. We know we can find the direction of motion of a particle by taking the derivative of the original vector function. But since we're looking for unit vectors, we should then divide by the length of the derivative. This gives us the unit tangent vector, a vector which points in the direction of motion and has length 1. Now, before discussing the other unit vectors, we need to first go over a fact, which is going to prove useful in a little bit. That is, if the length of a vector function is constant, then the vector function is always perpendicular to its own derivative. Now, this is a pretty sweeping statement, so it's always good to make sure why. Why is this true? We will prove this fact in a clever way by taking the derivative of the length squared in two separate ways. First, we have to remember that the length of a vector squared is just equal to that vector dot itself. And then, since the dot product is a product, we also have to remember to use the product rule. The second way is to remember that the length of this vector function is constant, and so the derivative of a constant squared is equal to 0. Equating these two methods gives us that 2r dot r prime is equal to 0, which means that r dot r prime is equal to 0. And if the dot product of two vectors is equal to 0, we know they are perpendicular. This fact alone actually gives us some mathematical insight into circular motion. Since the position vector from the origin to the particle always has length r, we know that the velocity will always be perpendicular. And the fact that the speed of this particle is also a constant is why centripetal acceleration is perpendicular to the direction of motion. Going back to our particle flying through space, using the unit tangent vector, we are able to find the direction of forward motion. But what about right? And what about up? We need a systematic way of defining these directions so that everyone working on the same problem has the same set of coordinate axes. And in particular, we want to make sure that these three vectors are perpendicular to each other. So the second unit vector I want to define is the unit normal vector, which will be the derivative of the unit tangent vector divided by the length of the derivative of the unit tangent vector. And this is where that fact comes into play. Since the length of the unit tangent vector is 1, and will always be 1 because it's a unit, we know that its derivative is perpendicular to the unit tangent vector itself. And therefore, the unit normal vector is also perpendicular to the unit tangent vector. This is our systematic way of finding a vector which is perpendicular to the unit tangent vector. As its name implies, the unit normal vector is always perpendicular to the direction of motion and points in the direction of the greatest curvature. Finally, we need to find one more unit vector, which is now perpendicular to both the unit tangent vector and the unit normal vector. Well, this sounds like a job for cross products. So we now define the unit binormal vector to just be the cross product of the unit tangent and the unit normal vectors. You may be wondering why we don't have to divide by the length of this thing, but it's because the unit binormal vector is automatically a unit vector. The length of b would be the length of t times the length of n times sine theta, where theta is the angle between the vectors, which is 90 degrees. And so sine of theta is equal to 1. So we have 1 times 1 times 1, which is 1. The length of B is always 1. Now, at any point along the curve, we can find a set of coordinate axes, one facing in the direction of motion, and two that are perpendicular to the direction of motion and also perpendicular to each other. This idea is very useful in physics, and in particular in relativity, as it allows you to set up inertial reference frames, a set of coordinate axes where your particle is at the center and everything else moves around you. Let's finish up with an example of how to find some inertial reference frames. Calculate the unit tangent, the unit normal, and the unit binormal vectors for the helix given at the points 3, 0, 0 and 0, 6 pi, negative 3. We start by finding the unit tangent vector. We take the derivative of the vector function and divide it by the length of the derivative. The unit normal vector is then obtained by taking the derivative of the unit tangent vector and dividing it by its length. Keep in mind that the derivative of a unit vector is not always a unit vector. We do need to divide by the length again. And the unit binormal vector is then just the cross product of the unit tangent and the unit normal vectors. Now that we have formulas for all three unit vectors, we can plug in our points. The point 3, 0, 0 occurs at the time t equals 0, and the point 0, 6 pi, negative 3 occurs at the time t equals 3 pi over 2. Plugging these values for t back into the formulas can give you the vectors that form inertial reference frames at those points.